Welcome everyone. We are going to have a discussion on relative atomic mass and then also relative molecular formula or relative formula mass. These are the concepts that we want to look at in this presentation. I hope you pay enough attention to basically understand these concepts from the one go, because understanding of these concepts is very crucial because it influences your understanding of subsequent concepts related to calculation of masses, of compounds, calculation of moles, calculation of the required mass to make compounds or to quantify compounds. So that means that it is a very important session that you're going to have here. So let's start with a concept called the atomic mass. What you need to know is that this concept can have several names, but you don't really need to get confused with these several names. We can call it atomic mass, we can call it relative atomic mass, we can call it the weighted atomic mass. Okay, those are actually several terms, but they basically mean the same, and perhaps we will understand why we are having all those names. Okay, so relative atomic mass, and then atomic mass, and then weight atomic mass. Actually, the fourth one could be average atomic mass. Average atomic mass. So this 1, 2, 3, 4. They are the same. Okay, they are the same concepts. They mean the same thing. Okay, so what do they really mean? Before we go to what they really mean, let's first see where we find this atomic mass. Where do we usually find it? We find this atomic mass when we are dealing with the periodic table. So the periodic table is here. You can see that this is not a periodic table. Just excuse me for that. You can cut that out. So where do we get the atomic mass? What are the figures before we understand what it is? On your periodic table, you have a number of elements. And on each element, usually there are two figures. There is a figure that is usually up here, and then there is a figure that is always below, which is this one. So the one below is what we call the atomic mass, and it is that figure that we are talking about. So we go back to understanding what it is. So each element is having its own atomic mass. So what is atomic mass? To understand what atomic mass is, we need to first of all know that an atom is actually very, very small. So determining its mass, it could be it is actually difficult. Okay, so carbon-12 is what I can say is used as a reference element for determination of mass of other atoms. Okay, so the mass of an atom, comparing it with a 12 of carbon-12, is what we call the atomic mass. Okay, so a 12 of the mass of carbon-12. The mass of the atom that you are perhaps investigating or you're dealing with, comparing it with the mass of 1/12, that is a 12 of the mass of carbon 12. That is what we call the atomic mass. So this is basically like saying, if you choose an element to be your reference point, so for every element's mass, you relating it to that mass of the reference atom that you have chosen to use. So in chemistry, a 12 of the mass of carbon 12 is what we consider as the reference mass that we can use to compare with the masses of other atoms. So this number is usually given to us. Okay, so we can always ask you what is the atomic mass of carbon, for example. It's 12, right? Or of oxygen, what is it? It's 16, right? These numbers, these atomic masses, are found on the periodic table. Okay, so you always go and check what is the number on the periodic table. And that number is the one below, just like what we have just seen for carbon. Okay, so that's clear. So we need to explain to you why we use the word relative. Here, for example, relative. Why are we using the word relative? Often when we use the word relative, it means that we are comparing it, we are comparing a given parameter with another. Okay, that's why that's the use of the word relative in sciences. Okay, so what is it in relation to? In relation to, and that is why we are saying that the mass of an atom in relation to the mass of carbon, to a 12 of the mass of carbon 12. Okay, this 12 here is basically to emphasize that it is the isotope carbon 12 that we are referring to, not any other carbon. Okay, carbon 12, that is what we are referring to. Okay, so we also go to why we use average. Okay, we have looked at why it is relative, because we compare it to the standard which we chose as our reference point, and then now we move to why we call it average. Now we have atoms that exhibit what we call isotopy. Isotopy is a concept whereby you have atoms of the same element having the same number of protons but different number of neutrons, and therefore they have different mass numbers. But all these atoms belong to the same element. So that means that you can have an element that has several types of as isotopes. The isotopes are the atoms of the same element that have the same atomic number by different number of neutrons, and therefore they have different mass numbers. Remember the mass numbers. The mass number is actually the number of protons and neutrons in the nucleus of an atom. Okay, I hope that is clear. So you know why we call it the average atomic mass. You know why we actually call it the relative atomic mass, and you also know the word atomic mass. Okay, so these numbers are usually given in the periodic table. You don't need to memorize them. Sometimes they have actually decimal points. Let's check that for carbon again, and we see if we have decimal points there. Yes, you can see carbon is 12.011, but in your calculations you always use 12. you just use the whole figure. There's no need for you to have this decimals that's in there. Okay, so when you put 12, that's fine. So the units for the atomic mass or relative atomic mass is atomic mass unit, AUM. Okay, those are the units that we use. Now we go to our second concept, and that is the concept to do with relative molecular mass and then relative formula mass. These are actually the same things, but there is a unique difference. When to use them. Actually, the calculations, if it is in terms of calculations, what would the answers? It's basically like saying that there is a way we should call some compounds, okay? But when we do look at the mathematics associated with determination of whether it is relative molecular mass, whether it is relative formula mass, the calculations are the same. So why are they any different? The difference comes in with what the type of compound are we dealing with. If we have what you call a molecular compound is basically formed when you have non-metals combining together. For example, hydrogen combining with oxygen to form water. Water is a molecular compound, right? Yes. So you can't say with water, it is more correct to say that I want to calculate the relative molecular, because the water is molecular, the relative molecular mass of water. If you say I want to calculate the relative formula mass of water, you cannot really be penalized as such, okay? But it could be perhaps not really okay for you to say, I'm going to calculate the relative molecular mass of sodium chloride. Why? Because sodium chloride does not exist as molecules, right? No, it's basically an ionic compound. So with ionic compounds, we talk about relative formula mass. Okay, so often you will basically see this a lot, but if you see this, don't get confused. Okay, so what are they? So we have looked at the atomic mass. Okay, it's basically the mass of an atom compared to a 12 mass of carbon 12, right? Now, so a compound is having several atoms of the different elements that make it up, right? So if we add the atomic masses of all the atoms in that compound, then we get the relative formula mass, or what we are calling the relative molecular mass. So the calculations are basically the same. It's basically which one is actually exact than the other in terms of the conventional way of communicating in chemistry. So let's go to this. So it actually is a definition in terms of if the masses still will refer to a 12 of carbon 12. Okay, so it is the mass of one compound compared to a 12 of carbon 12. It still remains the same, whether it is relative molecular mass, whether it is still the relative formula mass. Okay, we are comparing it. We are comparing the mass of that compound to the 12 mass of carbon 12. So the calculations for both is just add the atomic masses of the different atoms that make up that compound. That's the calculation there. So let's look at some examples here. So sodium chloride and calcium carbonate. These are the examples we are going to look at first. Okay, these are examples of the LME compounds. So let's look at. Please note that AR stands for atomic mass, and then MR, capital M, and then R stands for the relative molecular formula. Okay, O can also stand for relative formula mass. Okay, relative molecular formula. Okay, what we have seen here, just a minute. Relative formula mass or the relative formula mass. Relative formula mass or the relative molecular mass. Those two concepts there. They are all represented by MR. The M is capital, the R is a small letter. Okay, so let's calculate the relative formula mass for copper sulfate here. You need to write the chemical formula for the compound properly, okay, because it has some figures which we call subscripts, and they tell us the number of atoms of that particular element in that compound. So that means that if you don't write the chemical formula for the compound properly, you can never get the right relative formula mass, right? So still, the trick is you use your periodic table to get the relative atomic masses, the number which is always below the symbol of the element. So copper has the relative atomic mass of 63.5. Okay, 63.5, and then you have sulfur with the 32, and then oxygen with the 16. So you add the relative atomic masses, but also take into consideration the number of atoms that you have per each. So how many copper atoms do we have here? You have 1, so it is 63.5. Then you add, you go to sulfur. Sulfur is 1 atom, so that 1 atom is 32. We come to oxygen. Oxygen has 4 atoms here, so you have to multiply that 16 times 4. So the total that you get is the relative formula mass. Okay, that is the relative formula mass in grams. Okay, and then when we look at the concept of moles, you will see that we can talk about grams per mole. Okay, but for now we just keep it there like that. Sodium chloride. So how many atoms of sodium? 1. How many atoms are we having for the chloride? Is 1. So it is just the 1 for sodium plus the 1 for the chloride. So it is 23 plus 35.5, and you get this. Okay. Calcium carbonate. Calcium carbonate is the formula, the chemical formula is this. That is calcium carbonate. That is how you write it. So calcium is 40 plus the carbon, which is 12, plus the oxygen, which is 16, but the oxygen is times 3. So what do you get? You get 100. Okay. So let's look at One more concept. Do you have enough examples? I think so. We'll remove that out. Now, if you know the mass of each atom in a compound, then it means you can determine the proportion in terms of percentage of that atom in that compound. Let me repeat that. So you have, let us say you have water here, right? If you calculate the relative molecular mass for water, you have hydrogen, which is 1 times 2 plus oxygen, which is 16, you basically get 18, right? So in this water, the hydrogen is basically 2 out of the 18. So that means you can convert this into a percentage. So the percentage that you get is the percentage mass of hydrogen in the molecule of water. So this is what this concept is all about, calculating the percentage mass. So you need to first get the relative molecular mass or the relative formula mass for the whole compound, and then thereafter you pick the atomic mass for the compound you're looking for over the relative formula mass or the relative molecular mass times 100. This is the concept we have here. So copper, in copper sulfate, what is the percentage of the percentage mass of oxygen? So how do you do it? We have already calculated the one for copper. So we basically know the relative formula mass for copper. If we can go back here, we already have it here. We calculated it. Okay, so we know it. So this out of the one for oxygen, and the oxygen was in copper to sulfate is basically is basically 4 times 6. Okay, so we go back. Percentage, where are we? Yes, we are here. Okay, so we have 4 atoms of oxygen times 16 over the overall relative formula mass for copper sulfate. Is that clear? So let us calculate the percentage of chlorine and sodium chloride. So we know that chlorine is equal to 35.5, right? And then sodium is basically 23. Sodium is 23. So you add them to get to the relative formula mass for sodium chloride. So here you get 5, this is 8, this is 5, right? Yes. So that is the relative formula mass for sodium chloride. Okay, so out of this 35 is chlorine, and it's what we are looking for, the percentage for it. So it is basically 35.5 over 58.5. You multiply that by 100, and you get that the chlorine is 60.7%. in sodium chloride. So we also can come here. For carbon, we can also still determine that. For carbon is 12, oxygen is 16. So in carbon dioxide, you'll have 12 plus 16 times 2, because the oxygen, the oxygen atoms are 2. So here you get 44, right? So what is the percentage of carbon in carbon dioxide? It is the 12 over 44 times 100. So you get 27.3%. Okay, so that is where we are going to end. But what if you're asked a question to calculate the percentage of carbon in 2 grams of or 20 grams of carbon dioxide? Will the percentage change? Okay, will the percentage change? The answer is no. The percentage will remain the same. Okay, but its mass within that particular mass that has been quoted is what can change. So remember that the proportion, the compound is formed when elements combine with a fixed proportion or a fixed ratio. Don't forget that concept. Okay, so that's where we can end. We shall look at other calculations after this.